Everyone, and thank you for this wonderful conference. My name is Valerii. I'm from Institute of Continuous Media Mechanics, and the topic of this presentation will be related to strain measurement with fiber optic sensors. The presentation will consist of four main parts. So nowadays, fiber optic sensors gain huge popularity due to some of the advantages that they represent, such as the small size, which makes it possible to embed optical fiber inside of different kinds of material, their high sensitivity, immunity to electromagnetic interference, and the ability to operate in wide temperature range. There can be different kinds of classification of fiber optic sensors, and one of them is to divide them into single point and distributed ones. In our laboratory, we study among single point fiber optic sensors, fiber break gratings, and distributed sensors based on relay scattering. So the main difference between these two types of sensors is that single point sensors can measure strain or temperature change only in some localized areas of the optical fiber, which was preliminarily influenced by ultraviolet light or some other influence. And distributed fiber optic sensors utilize all the optical fiber as a sensing element. So fiber break grating works as an optical filter, and it reflects narrow wavelength spectrum. So if we input a broadband light into the optical fiber, most of the wavelengths of light will come through the break grating without any interaction with it, and only a small number of wavelengths will be reflected back, and we can measure this reflected spectrum, and we can relate the sheet of this reflected spectrum with strain or temperature change. Also, we can inscribe several break gratings inside of one optical fiber and interrogate them simultaneously by using wavelength division multiplexing. So here it is shown that we can use, for example, 5 break gratings inside of one optical fiber. So in general case, we have two equations with 3 unknowns to calculate strain components based on the spectrum shift. But in usually the actual stress state case can be applied, so we can rewrite these equations into one equation with one unknown, the longitudinal strain along the optical fiber, and it is related with the wavelength shift by the coefficient of strain sensitivity, which is usually equals to 0.78 for silicon glass optical fibers. Distributed fiber optic sensor based on relay scattering works a little bit differently, because in this case the light is not reflected from a huge change of refractive index, but it is scattered on small impurities in the core of the optical fiber, which leads to a small change of internal refractive index. So the main principle of measuring distributed strain with distributed fiber optic sensors is to measure the reflected ground. So it is the scattering distribution along the optical fiber length. On the first step, we measure 2 reflected grounds for the initial state and for the strength state. Then we choose a small window from this reflected ground on which we provide Fourier transform to calculate spectrum. And on the third step, we use cross correlation to calculate the spectrum shift. And we can relate the spectrum shift with the strain. So this is one point of strain, and then we can move this sliding window and do all these operations again. So we will calculate the strain distribution across the length of the optical fiber. By using these two types of fiber optic sensors, as for any kind of sensor, there is some measurement noise which the sensors represent. So we try to study the statistical characteristics of this measurement noise in the absence of any external influence or change of temperature. So we took 10 fiber break gratings, measured some strain without any external influence for some time, and statistically analyze this measurement data. So the main statistical characteristics of this of fiber Bragg ratings is that the standard deviation is around 0.9 microstrain, and the maximum amplitude of strain range is around 8 micrometers. So because these data obeys the law of normal distribution, most of measurements should lie within two standard deviations, so should lie in the range of 1.8 microstrain. And this means that this is the noise floor level below which we can't reliably measure strain. But in some of the cases, we want to, it is desirable to measure strain of lower level. And to reduce this measurement noise, one of the straightforward ways is to apply moving average filters. So we can choose the window and find average on this window of the data, and then move this average window to provide this filter. So it is shown that we can significantly reduce the noise, and using n average points, we can reduce the noise level by a factor of m. And another possibility is to use several fiber optic sensors, which can be located beside each other to reduce the measurement noise. And here on this slide, you can see how this moving average filter was applied to two conditions without any force applied and with some force applied with strain increase by step load. The same was done for distributed fiber optic sensors. And now we have not only the time dimension, but also the length dimension. And by analyzing the distribution of all this data that we measured, the statistical characteristics of noise is that it is around 2 times bigger than fiber Bragg ratings. But for distributed fiber optic sensors, we have more controlled parameters, which can be controlled programmatically. This is the gauge, so-called gauge length, across which we can calculate the strain. So we can reduce the noise level by increasing the gauge length programmatically. And the second part is about strain gradient measurement by this fiber optic sensor. So on this slide is a case of two composite specimen of different shapes, and by applying tension to this specimen, the strain distribution was measured by a single point and distributed fiber optic sensors, and it was also compared with finite element analysis. So you can see that the results of measurement are quite satisfactory, but in some of the locations where strain changes rapidly, it is still difficult to analyze strain even by distributed fiber optic sensors based on delay scattering, despite the fact that they have one of the best longitudinal resolution among all the sensors. So the strain gradient influences the measurement of strain in different ways. For example, for the single point Bragg rating sensors, it influences the reflected spectrum of such ratings. So we studied this influence. We took the shape of the sample, which by applying a load applies a huge strain gradient across the sensor line. And we used this experiment on 3 different lengths of the fiber Bragg ratings. And it is shown that applying different loads or applying different strain gradients, it influences the width of the reflected spectrum. It becomes wider and wider. And this means that it can be a huge strain measurement uncertainty of the limits of about tens or even hundreds of microstrain. And for the distributed fiber optic sensors, again, the gauge length, the so-called gauge length, should be considered optimally, because if we choose it very low, there will be too little data to provide Fourier transform, and we will have a lot of measurement noise, as shown here in red color. And if we took too big gauge length, so the cross correlation procedure will give a lot of artifacts, and we will have a lot of measurement errors too. So the optimal parameter is about 5 millimeters, 5 to 7 millimeters for distributed fiber optic sensors. And the last part of the presentation is related to providing distributed strain measurements in presence of fiber break gradients in the optical fiber. So the following experiment was conducted. We took the optical fiber and applied tension to 3 parts of this optical fiber, and one of the parts included 5 break gradients. And one of the parameters that can be optimized for distributed fiber optic sensors is the wavelength scanning range. So at the first step, we took the biggest scanning wavelength range that the reflectometer could provide, and it includes 4 fiber break gradients with bigger reflectance. And in this case, the strain measurement is not satisfactory because there are a lot of measurement noise and no positive data. So the next step, we decided to shrink the scanning wavelength range and to put it aside from the break wavelengths of fiber break gradients. So in this case, the 2 parts of the optical fiber that are tensed and doesn't include fiber break gradients provide good results, and the part of the optical fiber with fiber break gradients have some insensitive zones, which does not give us any information. So it was proposed to use hand window function to provide the periodicity of the studied signal, and this eliminates the spectral leakage that occurs due to the high reflectance of fiber break gradients. So by providing this window function, we can eliminate this insensitive zone and achieve good results on strain measurement by distributed fiber optic sensors. And it was shown that this can be done on an experimental sample with strain gradient. So it is shown here that the traditional algorithm of strain calculation gives us insensitive zones around fiber break gradients, and using the windows function, we can eliminate them and compare distributed fiber optic sensors with single point fiber optic sensors and give very similar results. So at the conclusion, the noise level of distributed fiber optic sensors and break gradients was estimated, and it was shown that strain gradient leads to spectrum broadening of fiber break gradient sensors and can be optimized for distributed fiber optic sensors, and it was proposed a method to measure distributed strain in the presence of fiber break gradient in the optical fiber. Thank you for your attention.